What we're going to be looking at in this video is we're going to be looking at some basic properties of acids and bases and talk a little bit about how we can identify substances that are acids and which are bases. So the first thing that we're going to do is we're going to give some examples and talk about some different ways that we can identify them. So let's go ahead and get started. So some common examples of acid solutions that you might know of. For example, gastric acid, which is actually a mixture of hydrochloric acid. Those are the acids that are in your stomach that help break down your food. Battery acid is another form that's usually sulfuric acid. There could be other forms of acid within there. Vinegar, which is acetic acid. So if you've ever used like balsamic vinegar or anything like that, it actually does have a mild acid in it. Citric acid is found in almost any citrus fruit. So that citrusy kind of flavor that you have, that's usually citric acid. And then vitamin C is actually an acid as well, and that its common name is ascorbic acid. Now, if I were to identify like how I would know a substance is an acid or a base, there are a couple different ways that we can do this. Now, there is a piece of paper, and it's called litmus paper, and it's a piece of paper, and what you can do is with that strip of paper is that you can dip it into a solution, and depending on the color that it turns, you can identify if this solution is acidic or basic. So if I were to use a piece of litmus paper on an acidic solution, if I were to dip that in that solution, it would actually turn red. Phenolphthalein is actually a dropper. It's actually a liquid, and you drop it into a solution and it will change the color of the solution. So say that I have an acidic solution and I add a drop of something called phenolphthalein, it will actually turn the solution a pink color. A universal indicator is something that you might see if you ever like had to identify the chlorine levels in a pool or something like that. It's similar to that, where you have kind of a rainbow of colors, and depending on what color it turns, you can identify the pH or whether or not it's acidic or basic. So if I were to use a universal indicator, the range for an acidic solution is between red and yellow. So depending on how acidic it is, you might get a slightly different color. Now, I have two theoretical definitions that we're going to look at, but we will be looking at these in a little bit more detail in the next slides. So there are two different definitions that we need to look at. The first one is something called the Arrhenius definition. And the Arrhenius definition says that an acid, it increases the concentration of these hydrogen ions. Now, those hard brackets around the hydrogen ions, that it refers to concentration. So when I said it increases the concentration, I know that it's talking about concentration because of those hard brackets. So it increases the concentration of those hydrogen ions. The Bronsted-Lowry definition is a little bit different. What it says is that acidic solutions are what are called proton donors. Now, notice I use the word proton. The word proton can be used interchangeably for hydrogen ions and that H+. And the reason why is because if you think about the atomic structure of H+, it actually is just a proton. H+ means it lost an electron, which means that a hydrogen ion, a hydrogen with a plus charge, is actually only a proton in the nucleus. So you will often hear me use these words interchangeably, hydrogen ion and proton, because they kind of mean the same thing. Let's go ahead and look at basic or alkaline solutions. Some examples of these. Lye, which is sodium hydroxide. Lye is something that's actually used in soap and things like that to make soap. Milk of magnesia. Milk of magnesia is, you can actually buy this at the drugstore. It's usually something that helps to calm your stomach. Ammonia. If you've used Windex, that really strong smell in Windex is usually going to be ammonia. Now, you can get some Windex that is ammonia free, but most glass cleaner actually has ammonia in it. And baking soda is actually a basic solution as well. Now, as far as our indicators, it is the opposite. And I just realized I made a mistake, you guys. I am so sorry. When I talked about acidic solutions, I said that phenolphthalein will turn it pink. It's colorless. So if I add this the drop of phenolphthalein to an acidic solution, it actually remain colorless. It's when I add it to a base that it turns pink. I'm so sorry for that confusion. What I have written down on the slides is correct. Now, if I have a piece of litmus paper and I dip it into a basic solution, it will turn blue. I like to think of this as basic is blue, so it will turn blue. Phenolphthalein, a drop of that in a basic solution, will turn it pink. Universal indicator, the color change is usually between a blue and a purple. Now notice that we have missed green. Green's usually right in the middle and we call that neutral. And we'll talk about that in one of the next videos when I talk about pH and calculating our pH scale. Now, if we talk about the Arrhenius definition says that a base will increase the concentration of hydroxide ion, so that OH, that polyatomic ion. And for Bronsted-Lowry definition, what we say is that a base is a proton acceptor. So we have a donator and we have an acceptor. So let's go ahead and talk about these two individual definitions in the next slides. So first, let's go ahead and talk about the Arrhenius definition. So an acid, as we saw in the previous slide, says that it increases the concentration of a hydrogen ion, or that proton. So if we look at the example and say that we had some hydrochloric acid and we were going to dissolve that in water, what we see is that it breaks up into ions. So we have a hydrogen ion and we have a chlorine ion. And as we can see, if that breaks up into ions, we are increasing the concentration of that hydrogen ion in solution because it does break apart. On the other hand, a base increases the concentration of hydroxide. So here we have an example. We have sodium hydroxide, which we saw in the previous examples. And if it were to dissolve in water, we would see that it breaks up into sodium and hydroxide. So again, it increases the concentration of that hydroxide ion in solution. So one big way that we can identify whether or not a solution or a substance is an acid or a base is by looking at what's there. Almost always an acid starts with a hydrogen ion, and we've actually used that definition previously when we talked about identifying substances. Sodium hydroxide, that hydroxide, almost all bases have a hydroxide in them. Now, not all, and that is where our Bronsted-Lowry definition actually comes into play, because it will give us an insight in where there is a base that does not have a hydroxide. Now, soluble hydroxide salts are strong bases and insoluble hydroxide salts are weak bases. So we can use actually our solubility rules to identify whether or not a solution is a strong base or a weak base. Now, if we were to actually mix an acid and a base, we actually would get our neutralization reaction. So if we were to mix our sodium hydroxide and our hydrochloric acid, what we see is that we create some sodium chloride, which is a salt, and we would create some water. And so what we see is that those acids and that base actually neutralize each other. And when we talk about pH, what we will see is that generally speaking, sodium chloride is actually neutral. It doesn't have a pH. And same with water. If we have clean water, we won't have a pH. So here we have, or it will be a neutral pH. It'll be a pH of 7. So here we have two things that are acids and bases, and we can actually neutralize them by mixing them. In general, when we mix an acid and base, we create a salt, or again, an ionic solution or ionic substance. In this case, the sodium chloride, and we will create water. So our definition of acids and bases, our second one, our Bronsted-Lowry definition. So in this case, what we have is we have an example of a reaction. Now notice that my arrows are going back and forth. And the reason why these arrows are going back and forth is that when I talk about hydrofluoric acid, this is actually a weak acid, which means that it doesn't break apart 100%. It doesn't break apart into all fluorine ions and all hydrogen ions and all of that hydronium. it actually still has some of the hydrofluoric acid at equilibrium or when it reacts. So it goes back and forth. There are some of all these substances when the reaction has stopped proceeding forward. So if I have my hydrofluoric acid and I mix it with water, what's going to happen is that the hydrogen ion or that proton is going to be donated to the other substance, in this case, water. So what we have is we have a fluorine ion, and then we have something which is H3O+, and this is actually called hydronium. This is actually a really important substance, and we use this a lot when we talk about acids and bases. I'm going to quickly label these, and I want to explain how I labeled these below. So what I did is by looking at hydrofluoric acid, seeing that actually donated a proton, so it's a proton donator, I can identify that as an acid. Now, that water, the other thing that it's reacting with, is acting as a base. And the reason why it's acting as a base is because it accepted that proton. So that A and the B stands for acid and base. Now the CB and the CA actually stands for a conjugate acid and a conjugate base, and we're going to define those in the next slide, so we'll come back to this and explain those. So let's go ahead and look at the base example that I have here. Notice that the base that I have here is ammonia. And notice that this also doesn't have a hydroxide attached to it, which is really important. And this is where our Bronsted-Lowry definition becomes really powerful. Because if we were to look at ammonia with the Arrhenius definition, we wouldn't identify this as an acid or a base because it doesn't have a hydroxide. However, when we look at how it reacts with water, we actually do see that it is a base because it accepts a proton. So notice that when we start at the very beginning, it's ammonia, and then it accepts a proton and becomes ammonium. So it is a proton acceptor, and therefore it makes it a base. So if I were to look at that, I would be labeling my ammonia as a base and my water as an acid, because my water is what donated a proton. Now, again, there might be something a little weird going on here, but I'm going to define some terms and come back to this example. So let's look at our conjugate acids and conjugate bases and some definitions of this. A conjugate acid-base pairs are compounds that differ by the presence of a proton or that hydrogen ion. All acids have a conjugate base, which is formed when their proton has been donated. So when you look at your acid and you take away that proton, what is formed is what's called your conjugate base. Likewise, all bases have a conjugate acid. They are formed after they have accepted their proton. So again, if you remember ammonia, it accepted a proton, and once it had accepted that proton and became ammonium, that is now called a conjugate acid. Now, if you go back to your example that we looked at, we saw that we had water. And water was actually reacting with both the acid and the base in two different reactions. And you might have noticed that water was acting differently in each example. And that's actually really important because water is something that is called amphoteric. And an amphoteric substance is a substance that can behave as an acid or a base. And it really just depends on what it's reacting with. So let's go back to the example that we just looked at on the previous page and kind of use these key terms to explain what we just saw. So again, if I look at this first example, hydrofluoric acid, what I see is happening is that a proton it's donating its proton. So this is my acid, and what it turns into is a conjugate base. Now, the reason why I call this a conjugate base and the reason why is because now this can accept a proton, which means that it can act as a base. So notice that we have an acid turning into a conjugate base. If this is an acid, water, therefore, is accepting the proton, and therefore water right here is actually acting as a base, and what it turns into is a conjugate acid. And because it has that extra proton, it can act as an acid right here. So we can see that's going back and forth. A conjugate or an acid will always have a conjugate base, and a base will always have a conjugate acid. Now, if we look over here, how do we know ammonia is a base? Well, we look at ammonia right here and we see what happens to it over here. What happens is that it accepted a proton. Therefore, based off of this definition, ammonia is a base, and here is its conjugate acid. If this is a base, let's look at water. Well, what happened to water was that it donated a proton. What does that mean? By definition, right here, water was acting as an acid because it was being a proton donor. So this is an acid, and here is my conjugate base. So you can kind of see that we have these pairs, and this is why it's called a conjugate acid-base pairs. Ammonia's conjugate acid pair is ammonium. Water's conjugate base pair is hydroxide. And again, notice that water is acting as a base and an acid. So it's acting as two different things. And the fact that it does that means that this substance is amphoteric. Depending on what it is reacting with, it can either be an acid or a base.